started on my laptop screen, ready for the Python scene. All those lines of text so clean, let's code and chase that dream. Python world, here we go. Write the script, let it flow.
In this video, we're going to be talking about debugging in Python. But before we get into debugging in Python, we need to know a little bit of background information. What are bugs, and what kind of errors might we encounter in Python? So first of all, to address that question, what is a bug? So a bug is an error or a flaw in a program that causes it to behave in an unexpected or incorrect way. Sometimes that can cause an error message to come up, or sometimes it means the results of your program are going to be incorrect. But where did this term come from? Well, the term bug has been around for some time in the context of engineering, usually to describe mechanical or electrical malfunctions. Most notably, Thomas Edison referred to technical issues in his inventions as bugs, dating back as early as the 1870s. But the first time the word bug was used to refer to a computer bug, or an issue with a computer, was in September 9th, 1947. And this was by the engineers working on Harvard's Mark II computer. And they found out that the machine had stopped working due to a literal bug, a moth, trapped in one of its relay switches. But what was the Mark II? Well, the Mark II was a massive computer. It was completed in 1947, and it was financed by the United States Navy, and it was used for ballistic calculations. It weighed over 23 tons, and it occupied over 4,000 square feet of floor space. You might think that might have been a really impressive, really fast computer, but it was actually quite slow by today's standards. It would take somewhere between 10 to 12 seconds to even compute a single logarithm. But it did do it automatically, meaning that it didn't need to have rooms full of human computers sitting there doing calculations. So it was still a great improvement. And here's another picture of the Mark II. In this case, it's showing someone operating it. And it would need a large team of operators. This would be a whole room-sized computer, and you need a lot of technicians to keep it going. And it was fed instructions using paper tape. This paper tape would have little holes in it, and that's how the data would actually be stored, as well as the program instructions. So nothing like what we're used to today when we're talking about computers. In any case, it was Grace Hopper, who's a famous figure in computer science history and a pioneer for computer science, who documented this incident and marked it as the first case of a computer bug. If you're not familiar with Grace Hopper, she was a computer scientist with PhDs in both mathematics and mathematical physics, and she rose to the rank of Rear Admiral in the US Navy. She's most notable for being the inventor of the compiler, a piece of software that takes our high-level programming languages and translate those into low-level machine code, saving us a lot of time and effort. We have her to thank for the idea of these high-level languages like Python that prevent us from having to write raw assembly. She's also famous for her work with the Harvard Marks I, II, and III, as well as creating the COBOL programming language. She's also the first person to write a computer manual. And she is quite well decorated, including her rank in the Army. She also has 40 honorary degrees, as well as ships named after her. She's an extremely significant figure in computer science, and someone to inspire to. In any case, to continue on with the story, this bug got trapped in one of the relay switches and stopped the computer from working. This led to Hopper documenting this in the logbook for the computer, as well as taping the moth right into the logbook there, and you can even see it says first actual case of a bug being found. So this is where we get the term bug from. So now that we know what a bug is, what kind of bugs can we encounter in Python? What kind of errors can we encounter? And we covered this a little bit in one of our first videos, but now we're really going to expand on it and explore some of the different bugs or errors you're likely to encounter. And the first type of errors are logic errors. These are logical flaws in the program's algorithm rather than its actual implementation or syntax. These types of errors don't cause the program to crash or return an error. Instead, they make the results of the program incorrect or for the program not to do the correct thing. And here we have a little example. What this program is trying to do is take 3 grades, stored in grade 1, 2, and 3, and calculate their average, and store that in average grade, and then return the result. However, when we run this program, we see a little issue. It says your average grade is 191.58. But that should set off a little red flag, because none of these grades are over 100, so how could the average be over 100? And that's because there's a logic error in this code, and it has to do with how we're handling order of operations. So when we see our programs run, we shouldn't just assume that because they ran, they're fine. We should actually think critically about the result we're getting here. So getting a result like this should set off a red flag and say, there's probably something wrong here. And as I said, there is, and it's with our order of operations. In this case, what we needed to do was put parentheses around the addition. Once we do that, we would get the correct result of 84.42. So these logic errors tend to be the hardest to debug because you don't get a nice error printout with a stack trace telling you where the error is. And they require a little bit of critical thinking to debug and even detect. Another common error you're likely to come across in Python are syntax errors. These occur when the Python interpreter encounters code that doesn't follow the correct syntax or rules. This can be really subtle things, such as forgetting parentheses, forgetting braces, forgetting brackets, as well as forgetting quotes and strings, things like that where you're getting the syntax of the language wrong. So here's an example where we're trying to print out the word hello world. But we forgot something here, and when we try to run this code, we get what we call a stack traceback. What this is it's a description of the error, as well as trying to tell us where the error occurred, or at least give us some hints at it. So when you get an error like this, when you're running your Python program, maybe you're working on an assignment or something like that, you shouldn't just give up and say, oh, something happened, I don't know what it is, I should ask for help. Instead, you should look critically at what you're seeing on the screen, because this is going to give you hints at what went wrong. And these are usually quite powerful hints. So let's try to break this down a bit and to see how we could read this error message. So the first thing we see is like file and then where the file is. When you have multiple files, this can be helpful, but for most of the programs we're going to be working on, they're going to only be one or two files, so it will probably just be one file that we're worried about. In this case, it's saying it happened in test.py. This was the name of the source file I tried to run. The next big clue is after that, it's going to have the line number it thinks the error occurred on. This isn't always 100% correct. Sometimes the error is actually a line or two before or after, but it should give us a general idea of where to look for the error in our file. In this case, it says line 1, and there's only one line in the file, so it's got to be line 1. The next thing Python does is it tries to give us a little hint about where on that line the error occurred. So in this case, it's pointing at the opening parentheses after print, and is trying to tell us there's something about this parentheses that isn't quite right. And if we look below that, it has a description of the error. This includes the type of error, in this case it's a syntax error, as well as a description of that error. And it says the parentheses was never closed. So that parentheses after print was never closed. So the way we would fix this is by adding a closing parentheses. So understanding these error messages and reading them carefully can get us some really big clues about how to fix our code when we encounter errors. So first step is always look at the line number it's talking about, look at the character it's pointing at, and try to read and understand the error message. This will probably be a great hint at what went wrong. Let's take a look at another type of error. So here we have indentation error. And as you might expect, this is errors related to the indentation of your code. Remember, Python uses indentation to denote code blocks. So if you don't indent this code correctly, we could get an indentation error. This could be a result of inconsistent or incorrect indentation. Let's take a look at an example. Here we're trying to do a for loop that runs from 0 all the way up to 4. And we want to print out each value of that in the for loop. But we kind of messed up the indentation here. We forgot to indent our print command. So if we ran this code, we would get an error message that looks something like this, which says that we have an indentation error. So again, if we look at this carefully, it says line 2. So that means we should be looking at line 2 in our code. And it's saying on line 2, it has to do with this P. Remember, this isn't always exactly where the error occurred. It's something around here. The big key is reading the error message. So it's an indentation error. So we know it's something to do with the indentation. And it says expected an indented block after the for statement on line 1. And if we look at this, yes, indeed, we are missing our indentation after the for statement. So the way we would correct this is by adding a tab, or more accurately, 4 space characters, to indent print. Next up is the name error. And this can result from attempting to use a variable or function that hasn't been defined, or it can also happen if we have a typo in our variable or function name, and Python thinks that that variable doesn't exist because we spelled it wrong. Here's an example, and in this example, we're trying to print out the value of a variable named value. But the issue is value hasn't been defined anywhere. If we're going to use a variable, we need to at least assign it a value first. If we don't, we'll get an error that looks something like this. So in this case, the error message has the most information, says name value is not defined. Python also tries to help us sometimes with a hint like, did you mean false? In this case, the hint's wrong. The issue was we never gave value of value. So if we wanted to do this, we would have to define value somewhere in our code. Next up is the attribute error. And this is a very similar error to the name error, except it's for when an attribute or method doesn't exist for a given module or object. That might sound a bit confusing, but you may recall that we've been using a few different string methods on our strings. Things like the replace method, things like count method, as well as things like strip, and of course, lower and upper. If we spelled one of those names of a method wrong, or if we tried to use one that doesn't exist, we would get an attribute error. Let's look at an example. So in this case, we're declaring a string called hello world, and we're storing that in myString. Then we're trying to append something to a string. And what we're trying to append is how are you, and we're trying to use the append method. But there's a problem here. And if we were to run it, we would get this attribute error. And a big hint here, other than it being on line 2, is that it says string object has no attribute append. What this means is there is no append method for string objects. Remember, strings in Python are immutable. So there's no method to add to a string, because all you can do is create a new string with the text added. So instead of saying myString.append, we'd have to say myString plus equals how are you. We'd have to create a new string with that text added to it. So it's always important to make sure that you have your method names incorrect. And when you get an attribute error, it's probably referring to you getting a method name incorrect. Next up is IndexError. And this error can happen when you're trying to access an index that doesn't exist in a sequence being a collection that is ordered in some way. So like a string that has ordered characters, a list that has some sort of order of elements, or a tuple. The issue is we try to give it an index to access a specific member of that sequence, but that index doesn't exist. Maybe we're out of the bounds. We've gone too far to one end. Let's take a look at an example. Here we have a string, just hello, and we're storing that in myString. And then we're trying to print out a specific character in that string. In this case, that would be the character at index 10. But we get an error when we try to run this, and this would be an index error. We know it's on line 2, and the big hint here is it says string index out of range. So in this case, the word hello only has, 1, 2, 3, 4, 5 characters. So that means it's going to have indexes 0 to 4. So 10 is way out of that range. So if we try to access something at index 10, which doesn't exist, we get an index error. This is always why it's important to make sure you understand the size of the collection when you're trying to access specific elements, so you don't go outside of that range. Next are type errors, and these occur when an operation or function is applied to an object of an inappropriate type. And you've likely probably encountered one of these while you're working on the labs or working on assignments or examples, especially when you're trying to input text from the user as a string, and then you want to use that text like a number, like adding to it, or performing some sort of mathematical operation on it. That doesn't work because a lot of mathematical operations can't be done on strings, so you get a type error. Same thing could happen when you're trying to add to a string. Trying to add an integer value to a string won't work. You'll get a type error because the types are inappropriate because we didn't convert them first with casting. Let's take a look at an example. Here we're asking the user to input their age using the input function. Remember, the input function returns a string. So we have a string value stored in age, and then we're trying to calculate a result of adding 5 to that age. But we get an error. Again, other than it saying line 2, the big hint here is the error message that says can only concatenate string, not int to string. And this is a fancy way of saying that you can't add an integer to a string. They have to be the same type. So if we wanted to fix this, we would have to convert that 5 to a string. The last error we'll look at is the value error, and this occurs when the value we're working with is of the correct type, but for some reason it has an inappropriate value. Let's look at an example. Here we have a case where we have the text hello in a string, and we're storing that in user input. Then we're trying to convert that string user input into an integer value and store it in age. But there's a problem here. And if we run this, we'll see that we get a value error, saying invalid literal for int with base 10 hello. So that text can be confusing, but if we look at the other hints, line 2, as well as where it's pointing at, we can see that the issue is probably because the int function is trying to convert the text hello. And that doesn't really make sense. Hello isn't a number, so we can't convert that into a number. Then we get a value error. So when you get these errors, it is important to read these messages closely, take a look at the line they're talking about, take a look at the characters they're pointing at, and read that error message, and see if you can work from there to figure out what's going wrong. Another debugging technique is to actually just Google the error message. That might seem a bit silly, but there is a lot of documentation out there about all of these different types of errors, as well as a lot of people on sites like Stack Overflow that have had similar problems to you, and the solution may already be out there. It's not against the rules of the course to look up error messages, as long as you're not copying other people's code. So I do highly recommend using Google. There are many other types of errors in Python, and you can find a full list if you're interested here of all the built-in error types, but I don't necessarily recommend just reading through them. This is a much better resource if you're encountering a new error type that you haven't seen before and you want to read more about it. Another great resource is this free book that I linked to here that explains some of these errors in more detail with more examples. So now that we've seen several different types of errors, as well as bugs we might encounter in Python, how can we debug these? What techniques can we use to identify these bugs and eliminate them from our code? So we're going to get started with some very general tips, and these should be applicable to most programming languages. The first is start simple. Focus on small, isolated parts of the code. And in general, this is great advice for programming. You should try to break up problems into smaller parts and solve those smaller parts and then integrate them together, rather than just writing the whole program in one go without testing or debugging. So we want to focus on small parts of our code where we know the issue resides, rather than trying to debug a massive program all at once. And it's best to do this as we go by breaking the problem into smaller parts. Next are read error messages carefully. And we just talked about this a bit, but those error messages have a ton of detail. This is true of most programming languages, and Python has some great text in those error tracebacks. So make sure you're reading them, checking the line numbers that they state, as well as the messages they provide, because these will be a great hint at what went wrong. Next are check for common error types. And some big ones are misspelled variable names, and also remember that Python is case sensitive. So a variable name with a capital letter is going to be different than a variable with a lowercase letter. Also check for incorrect indentation, as well as off by one errors. That would be where your loop is running for one less or one more than when you think, for example. Next is comment out sections. So those comments that we've been seeing so far to document our code can also be used to comment out actual lines of code so they're ignored by the interpreter. This is great because it allows us to temporarily disable parts of the code to isolate certain sections. Maybe it's a section that we're not looking at, or maybe it's a section that we suspect has the bug in it. So by using comments to remove lines of code, we can temporarily remove them, make sure they're not executed, but we don't delete them from our file, so it's easy to bring them back by just removing the comment character. And lastly, test incrementally. So when we write our code, we want to do it in small chunks. Also, when we're testing it, we want to test it out in small chunks. Like I was saying, we want to break big problems into smaller, easier to handle problems. The next technique we're going to look at is rubber duck debugging. And this is a debugging technique where when the programmer is faced with an issue or a bug, they take a step back and they try to explain their code, line by line, out loud to an inanimate object, such as a rubber duck. Though really it could be any object or even another person. And the hope here is to identify issues as we explain our code like we were teaching it. So here's how this method works. First, we beg, borrow, steal, or otherwise fabricate a little rubber ducky, bathtub variety. Then we place it on the desk in front of us and inform it that we're just about to go over some code with it, if that's all right. Then you want to explain your code to the duck and say what your code's supposed to do, and then go into detail and explain your code line by line. At some point, you're going to tell the duck what you're doing next, and then realize that's not in fact what you're actually doing, and the duck will sit there sincerely happy in the knowledge that it has helped you along your way. Now, that might sound really silly, and it is a little bit silly, but the idea here is that when we approach our code in a new way, almost like we're a teacher explaining it to someone, and we go step by step through the code, explaining each line, eventually we're going to get to a line where we say what it does, and then it's going to click in our head that what we said isn't actually what we're doing. We're actually doing something different. And then we will have found the point in our code where the bug likely resides. So let's try to actually put that in practice and debug a program. We're going to start with this program here on the screen. So what this program should do is it should input numbers from the user until a negative number is input. And then it should take the sum of these numbers and output that as the total at the end of the program. But it has a bug in it and it's not doing what we want. When we give it a run, it will look something like this. Maybe we put in 10, 25, 100, and then -1 to exit. But the issue here is we get 100 as the output, which makes no sense. 10 plus 25 plus 100 is definitely going to be more than 100. Again, we should be thinking critically about what our program's outputting. Just because it didn't crash or have an error doesn't mean it's right. So how could we debug this using rubber duck debugging? Okay, I got my duck here. So we're going to try explaining this to the duck. So the first line is total equals to 0. And that's setting the variable total equal to 0 and declaring it. Our next line is going to be inputting values from the user. We're going to ask them to input a positive floating point value or a negative number to quit. Then we have to convert that to a floating point value because we want to add this to a total. So we're going to use the float function for that. And then we store that value in num, declaring the num variable. Next up is the start of our while loop. And the condition for our while loop is num greater than 0. So if the user input a negative number, it's just going to exit the loop and we're not going to run it at all. But we're going to pretend now that they input a positive number. So we enter the loop. Next, we are trying to add num to total so we can keep track of the total as we go. But wait a second, that doesn't say total plus equals num, that just says total equals num. And that's where our bug is. We made an error here and we forgot the plus sign. So we're not actually adding to total, we're just resetting total to num each time. And that's why we got 100 in the last run of that program, because that was the last value we input that was valid. So it simply set total to that. So the way we would fix this is we would add a plus sign here. So that is the idea here. We're going to go line by line from the top of our code, or at least the area where we think the bug is, and explain it out loud to our duck. But to be honest, it doesn't really have to be a duck, and it doesn't even have to be out loud. The idea is you're just going line by line and explaining it, even if it's just in your own head, what that line does. And eventually you'll find a line that doesn't actually do what you think it does. Like in this case, we found that we were setting total equal to num rather than adding num to it. The next technique we're going to look at is using the print function for debugging. This is a very common, quick, and easy technique, and the idea here is that we're going to use the print statement to output the value of different variables, as well as to track the flow of execution. So we want to put the print statements at strategic locations in our code that have important operations occurring before them, different state changes, or we just want to know, is our code actually getting there before like this error occurs? Or are we actually entering this if statement? Are we actually entering this loop? By putting print statements there, we get some output to the console to let us know if that print line was actually triggered, and if it was, what values it's printing out. So what are these strategic points? Well, that can change program to program depending on what you're doing, what your bug is, but some good ones, as general rule, are before and after loops, inside conditional blocks like if statements, and at the beginning, middle, and end of functions. So let's take a look now at an example of where we can use print debugging. So here we have a program, and it's supposed to find the sum of all of the even numbers between 1 and 10 inclusively. So we want to go through all those numbers, see if they're even, add them to a total, and print out that total. But if we try to run this code, we would see we get an incorrect result. Again, I should stress you need to be critical of the results you get. Just because your program runs doesn't mean it's a correct program. It could be outputting some gibberish. And in this case, 25 is incorrect. The way we could check is we could write out all the even numbers between 1 and 10 inclusively, 2, 4, 6, 8, 10, and add them together, maybe using a calculator. We should see that the correct result should be 30 and not 25. So how do we debug this? Well, one way we can debug this code is by adding print statements. And we've added a few here. So the first one we added was before the loop, and it's going to say total before loop, and then output the total. We added one inside the start of the loop, and it's going to tell us the current value of I, the index of the loop, as well as total. And we're going to add one inside the print statement, just to let us know if the print statement has triggered. These print statements for debugging can also be helpful not just to output values, but to also let us know we've reached a certain point in the code. We know if it says adding I to total, that this if statement has evaluated to true, at least for this loop, and that this code was executed. The last one we're adding is at the bottom here, and it's going to say values at the end of the loop, and it's going to tell us what I and total are. So we're targeting both before and after the loop, as well as some key points inside the loop. So if we were to run this code now, we would get a whole bunch of text that looks like this. And to understand this text, we have to understand which line corresponds to which print statements. So this first line up here that says total before loop is for that line we added before the loop. And this value down here that says values at the end of the loop is for that print statement we added at the end of the loop. Everything in between are those print statements inside the loop, and they happen multiple times because the loop runs multiple times. So let's go through this and try to understand what happened here. So we get total before loop is 0. Makes sense. We've just set the total to 0. Shouldn't be anything surprising. Then we enter the loop and we start printing out these commands inside the loop. The first one is in loop I, it says I is equal to 1 and total equals to 0. So it's starting with I equals 1 makes sense. We're starting the range at 1, and that range function is inclusive for the start. And total still equals to 0, which makes sense. We haven't done anything yet. So what happens next? We're getting add I to total, but we're only supposed to be adding even numbers, and 1 isn't even, so that's peculiar. The next line is in loop I, it says I equals 2, and total equals 1. So this means the loop had to have restarted, the value of I was incremented to 2, and now the total is 1. So it did add 1 to our total, but again, 1 isn't an even number. But 2's even, is it going to add that? Well, when we look at the next line, we see that it didn't say adding I to total. That means that if statement didn't run. It didn't treat 2 as an even number. That's another big hint. Instead, we get the loop restarting. Now I is equal to 3, total still equal to 1, it didn't add 2. And now we get adding I to total again. So it's treating odd numbers like they're even, and it's only adding the odd numbers, and it's treating even numbers like they're odd. It's not adding them. So this might hint strongly at there being an issue with the if statement, because it's not making that decision correctly. Is this even or is it odd? It's getting that wrong. And if we were to look closely at this code, we might then, as our next step of debugging, add some more print statements, but target in more on where we think the issue is. In this case, we think that issue is with the condition for our if statement. So what I did here is I added a print statement that is going to basically print out the evaluation of that condition. It's going to print out what I mod 2 is. So if we run this again, we're going to get a little bit different output because we added a different print statement. We also removed the print statements at the beginning and end of the for loop because they're probably not useful for debugging after what we just saw. So if we run this again, we're going to get this output. So again, we should look through this carefully. So this first run here is the first run of the loop. It's saying in loop I, 1, total 0. So the index 1, total 0. And I mod 2 is evaluating to 1. And then it's adding I to the total. And that sort of makes sense. If I mod 2 is 1, then 1 equals 1, so the loop the if statement rather, should run. But that's not what we want it to do. We want it to add only even numbers. So what happens next? So the next iteration of the loop is represented by these two lines. So we're saying I is equal to 2, total is equal to 1. I mod 2 is 0. But 0 doesn't equal to 1, so we don't call that line saying add I to total. So if you're reading this closely, you shouldn't be too surprised about the next line, where it says I is 3, total's 1. I mod 2, so 3 mod 2 is equal to 1, and then we add it to the total. So what's going on here is we got the condition of our if statement wrong. Saying I mod 2 equals to 1 is how you identify odd numbers. It's not how you identify even numbers. You can see an even number like 2 mod 2 is returning a 0, but odd numbers like 1 and 3 are returning 1s. So we got the condition of our if statement wrong here. And the way we can fix that is fairly straightforward. So to fix this, we need to fix the condition in the if statement. And we can do that simply by updating it to I mod 2 equals 0. And this is the correct way to detect an even number. Any number divided by 2 will have no remainder if it's even. And remember, the mod operation, at least for positive numbers, gives us the remainder. So if we change that from 1 to 0, and now we should be adding even numbers. And when we run it, we can see the total we get is indeed 30, which is correct. So let's quickly summarize. In print function debugging, we have to add print statements at key strategic locations in our code to give us an idea of what the current value of variables are, what certain expressions evaluate to, like we saw with I mod 2, as well as just a general notice if we've entered a certain block of code, like how we had a print line in that if statement. Combining these together in a strategic way can give us a lot more information about how our program's running. Just remember, it's usually good practice to remove those lines after you're done debugging. You don't want to have this big mess of print statements in your final product. So far, we've seen a number of general debugging techniques, including reading error messages carefully for clues, using rubber duck debugging, as well as print statement debugging. And these are all great because they're generally portable to other programming languages and environments. Regardless of whether using Python, C, or Java, these techniques will still apply and be useful to you. However, there are more powerful debugging tools that we have access to, but these tend to be more language specific. And the first one we're going to take a look at is what's built into Python. So PDB is Python's built-in debugger, and it allows us to do some very useful things, like pause the execution of code, step through code one line at a time, and inspect the current values of variables. So this allows us to do things like pause our code, run it one line at a time, and see how it changes the state of the computer's memory, what variables are available, and what the value of those variables are. Now, PDB might work very differently than what you're used to. It's very much a terminal or console-based command, which means it doesn't have a graphical user interface and can be a bit harder to use. Instead, you interact with PDB using keyboard commands. So let's take a look at what execution of this might look like. And at the top here, we can see that we're running PDB by saying python-m, which is for module, and then we're saying PDB, which means loads PDB, the debugger, and the name of the program we are debugging. In this case, this is example 4a that we saw before, where we're trying to add a number of even numbers. And in green here, we can see the different commands the user's inputting. What happens is the program starts running example 4.1, and it pauses right away at the first line, which was a comment. The user can then use the N command on their keyboard to proceed to the next line of code. So they hit N and it proceeds to the print line. They hit N and it actually runs that line, and then they get to total. They hit N and it actually adds to total, and they start the loop. And then they can issue another command to print out current values. Here we see P, which is print the current value of a variable. In this case, they're printing the value of total, and the output is 0. They then use a combination of N and P to go through that loop and print out values that are currently available in the loop. At the end here, they use C to continue until the next breakpoint or the end of the program. Now, as you can see, this is a bit complex, a little bit hard to use. So we're not going to be going into PDB too much in this course, because there's much better ways to do debugging in Python with the tools we already have available that are much more visual. So don't worry too much if this was confusing. We aren't going to be testing you at all on PDB. As I mentioned, there is a much easier to use and more powerful alternative to PDB, and that is debugging with PyCharm. And this is more what we expect you to use in this course. So PyCharm is a fully featured integrated development environment, and part of that is a debugging environment. Unlike PDB, PyCharm provides a richer and more user-friendly visual debugging experience with a complete graphical user interface. And this provides a few key features that will be important to us. And the first are breakpoints. I already mentioned breakpoints briefly, but what these are points we can set in our code that tell the debugger to pause at this point and allow us to inspect the current values of variables, even modify them, or step through the program one line at a time to get an idea of how everything's working. Next is the ability to step through code. This allows us to step through our code one line at a time so we can see how it executes and change the state of different variables as we go. It can also do advanced features like step into or over functions so we can see how those functions actually work and affect our code. Next is Variable Explorer. And this is a tool that allows us to inspect and even modify the value of variables while we're actually executing our code. So once we reach a breakpoint and pause, we can see what the current value of variables are and even change those values. And lastly is the ability to inspect the call stack. So we haven't gotten too much into functions yet in this course, but the call stack basically represents the path we took through different functions and how functions call other functions and call other functions and so on, and allow us to trace through those chains of calls to see exactly where our bugs are occurring and how the code is being executed. So this all sounds really great, but how do we actually run our code in a debugging environment in PyCharm? Well, typically you'd run that little play button or run button, but instead, when you want to run your code in debug mode, you click the debug icon or Shift F9 on Windows to run your program in debug mode. So this looks like this icon here that I'm showing on the screen right now, and you can find it right by that run button in PyCharm. And when you run your code in debug mode, instead of getting the typical console, you'll get the debugging environment that looks something like this, shown on the bottom of the screen here. This environment allows us to access all of those great features that we saw in that last slide. And if you're interested in how to debug your code using PyCharm, as well as how we can access all of those great features, please watch the next video in this series where we'll dive into the debugging environment, as well as see an example of how to debug a program using PyCharm's built-in debugging environment. But for now, that's all I have for you in this video. Thank you for watching, and have a great day.